Does the sound work? I think the sound works. Does the sound work? Okay. All right. Hello everyone, and welcome to the Sunday Valcon stream, where we continue where we left off yesterday. We'll fix a couple of things, rework a couple of things, and then improve the efficiency of our culling, and try to get to implementing level of detail support so that we can render very large scenes. So let's start with seeing where we are. So yeah, so this is kind of where we left off last time. There's like a lot of meshes on screen. They are different kinds of meshes. We are pushing a lot of triangles. The process is entirely GPU driven. And that's kind of it, right? The two issues are basically, so one is, even if culling hypothetically culls away everything, we are still spending some time in the GPU command processor processing empty draw calls, because right now we're not, like when we call away a draw call, we just say, hey, yeah, can you render an empty draw call? So processing that takes some time. And then the second issue is we are pushing a lot of triangles here, but we don't need to be. If we had LOD, we wouldn't push as many. Oh yeah, I guess the other issue is the triangle number that we have here is now not correct, because we are computing this on the CPU, and CPU just doesn't have enough information anymore to know. Before we start fixing this, or like improving this, I realized yesterday that there was one problem that I forgot about in our culling code. Let me add a thing that I probably should have added anyway, which is, let's add a key that can toggle culling. Wait. So that I can show you the problem, and then I can fix the problem, and then it'll be obvious that the problem is fixed. So we could like not render the we could like use a different compute shader or something like this to disable culling, but for now, what's going on today, to make it easier on us, we'll just say that, so if the frustum planes are 0, then culling essentially doesn't work, as in it treats meshes as visible. So let's just say for now that we'll do this. Yeah, so there's a to comment I left for myself. And let's see what the results of these are. So now when I press C to disable or enable culling, we can see that when I disable culling, performance is like 8 times worse, which is encouraging. This means our culling works. But B, you see that there are objects, and let me change the draw call count to be slightly less aggressive so that it's easier to see what's going on here. Yeah. Alright, so you can see that when we disable culling and enable culling, there are some meshes that are still rendered. Sorry, that are like not rendered. Basically, when we enable culling, it culls away some meshes that would have been rendered otherwise, which means our culling code has bugs. So yeah, I completely forgot about this yesterday, but when you build frustum planes out of the projection matrix equations, you're supposed to normalize them. Like, you can think of the plane equation of the first 3 numbers in the plane equation as being the normal of the plane. Now, normalizing isn't important if you only care about which side of the plane points are on. So if you are doing like X-line bounding box culling, it's generally unimportant. But we are doing sphere culling, and in our shader somewhere, we can see that the equation doesn't just look at the sign of the dot product with the plane equation, it also looks at the magnitude, right? And so what happens is that our planes are normalized and we have objects that don't that are visible but are still being called, right? So let's fix that. Basically what you need is you need to like normalize the plane equation by making sure that the length of the first three components as when expressed as a 3D vector is 1. So let's just make a function for this to fix that. The other thing I discovered yesterday is apparently GLM has a configuration bit that makes it more debugger friendly. I will try to flip this. But yeah, basically what we want is we want to divide P by the length of the first 3 components of the plane. And that should make sure that our culling is conservative, aka works. Yeah, so now when I press C, I still get substantial performance benefits. It's also like 6x or something like that, but the picture doesn't change, so that's good. We should probably also add so let's restructure the printing layout. Alright, and also let me check this GLFW, not GLFW, I was confused, this GLM macro. So the thing I was complaining about yesterday is that if I put a breakpoint here and I try to look at the frustum values, it's like not, there's like a lot of numbers here and I don't care about most of them. I think I found a thing in GLM source, which is this variable that I should be able. So basically, I think if I define this thing in my project file, then things should be more usable. Oh, great. How? Wait, hold on. Okay. It saw that Visual Studio doesn't wanna, but okay, doesn't want to show me the preprocessor macros in a friendlier fashion, but I guess I shouldn't be terribly surprised. So yes, let's rebuild with that. Let's see how that works. Hopefully that's good. And then we can actually start working on the things that I want to work on the stream. Let's see. All right, nice. So that's way nicer, right? Now you open up the vector 4 and you see, okay, here's 4 values. The other thing that I thought that maybe I want to do, and I might as well do it now, is I'm tired of typing the GLM prefix, but also we should probably, oh wait, no, add like a separate header where we include all things GLM. Let's call it mathage. So basically all of that, right? No. Oh, I guess we could have defined the GLM macro here. That could have been nicer. Oh well, too late now. Or maybe not too late. Although I guess it might change the ABI. Whatever, I'll keep this here for now. And I kind of want to do, I don't want to do using namespace GLM necessarily, but I guess I want to do using GLM vec3, vec4, mat4, and quad. And I guess that's it for now, right? Because I don't want to keep typing GLM everywhere. So now we can just include this. And let's just do a search and replace and see if our code still compiles. Right, so there still are like radials and stuff, but for this I'm happier to qualify these calls. We could do using namespace GLM, but I don't know what else I would be pulling in, so I think this is good for now. Alright, so now that we have fixed the culling, I want to tackle the, I wanted to do one more sort of simplification thing. Yeah, so before we do the more optimal culling setup, let me talk about one more thing that I thought we should do. We kind of did the thing on stream yesterday, and I thought about how we're gonna do level of detail stuff, and it's slightly painful to do this in the current setup. It's not too painful, but it's like there's a thing we can do to make it slightly simpler. So I wanted to talk about this, which I will. So, do I want to commit this? I guess I want to commit this first. Oh, why am I here? Since we don't need to qualify things with GLM : for many objects anymore, it might be easier. It might make it easier for us to reuse the structures between C++ and shader code, which is always nice. Qualify GLM names for most types. Also fix culling bug. Culling bug. We forgot to normalize our plane equations. Alright, so yesterday I added this thing in the task shader that said, hey, if the index of the task, if the index of the thread, basically if we are trying to process a meshlet that's out of bounds, then just skip it, right? And there's something similar here. And it is correct to do that, but it makes it slightly, this means that we have to also use the meshlet offset here and here. And I kind of wanted to get rid basically of this meshlet offset because, or not get rid, but not use it, stop using this in the task shader, because it will make things slightly, ever so slightly easier for us. But I realized that I sort of skipped one of Arctic Fox. When we added this, I thought, hey, we'll add this for correctness, but I forgot that actually also the thing that we added helps with performance. And I want to talk about why, because this is related to some of the previous stuff that I have said on stream last week. So let me switch to Arctic Fox. I think Arctic Fox is a bigger mesh. Oh, it rebuilds everything again. Does it like depend on command line arguments or something? This is weird. Anyway, yeah, so Arctic Fox is a bigger mesh. So let me... Bigger as in the bounds are bigger. Alright, this is... Well, now I can draw more of these guys. Alright. Should I draw even more of these guys? Alright. I'm hoping the video feed doesn't freak out because of this. I don't know if it doesn't. Let's see. Doesn't seem terrible. Yeah, so so we are rendering, we are like submitting, what is it, 100,000. Does Visual Studio support this yet, by the way? I wonder. Ah, this is the future. All right, yay. This is C++ 17 or something. I think, or 14. Who knows when this was added? Maybe it's even 11. But yeah, this makes long numbers much easier to read. So we are drawing 100,000 foxes, right? And each fox, I forgot how. I guess each fox is like, what is it, 1.7k triangles or something like that. So let me remove this meshlet offset check from here for now, which will mean that we are technically processing out of bounds meshlets, but hopefully nobody notices. And the other thing that I want to do is disable vsync to get accurate, stable timing measurements. So yeah, so right now we are rendering this at like 3.9 milliseconds without this if, and and also 3.9 with this if. Wait, this did not go as planned. Oh, I guess. Damn it. It's the same thing where I want to show something performance related and it actually doesn't want to be shown. Why is... Oh, sorry, I didn't mean to use... Sorry, I meant to use... Like, Arctic Fox isn't too bad, I suppose. But I wanted to use a way more aggressively simple mesh. Let me do that. I want to use something super small. I don't know, do we have like some... Yeah, cornel box. Hold on. Dutch rose. I have no idea what Dutch rose is, but let's use that. Alright. Let us remove that, I suppose. Okay, alright. So, and now we are rendering things very fast, so let's add another 0. Okay. So we are rendering, we are pushing a million objects and then we are culling a lot of these guys. So my guess is we are pushing like 150,000 objects or so after culling. And then a lot of these meshes are actually culled away. So this is actually a great scene that we can use to optimize culling as well. Maybe to make things slightly less crazy, I will do that. Well, I guess things are more crazy, whatever. So now, so this is rendering at 8.2 milliseconds. Now let me comment this out and hopefully I will actually see the difference and I can talk. Okay, yeah. So when I comment this check out, I have 11 milliseconds, right? So this check isn't just helping correctness, it's helping us with performance. So the reason why it does is that these meshes are super tiny. I don't know how like how many triangles there are in this mesh, but my guess is not very many. Let us check. Oh, great. Oh, right, we have... I don't care. No, I don't care. Can I like skip an assert? Oh, Visual Studio. You cannot skip assertions in Visual Studio. Yes, like validation layers don't like our vsync stuff because reasons I talked about this before. So let's look at the mesh. We have 5 of them somehow. How did that happen? Oh, it's debug. Man. Let me actually save this for later. Alright, so yeah, so temporarily we'll switch to this dash rows mesh because it's actually convenient for profiling like lots of meshes, right? So there's one mesh and it only has one meshlet, right? However, when we are running our task shader, the task shader processes 32 meshlets, right? So you might think, hey, yeah, obviously this if is important for performance because you have a task shader that runs a warp of 32 threads, and then only one meshlet needs processing, so this if is saving us time to compute this stuff. But no, this is not what happens, so let's replace it with something that's less obviously a branch. And let's just say that we'll accept the meshlet only if it's in bounds. Oh, and this is debug build now. Well, whatever. So it's still running at like 8.8 or whatever it was running at, right? So this is important for performance because when this check isn't done, then if you only have one meshlet, then we are still generating potentially 32 meshlets worth of workload for the rasterizer, because after this meshlet there is other meshlets in the buffer, and then they all go to the rasterizer and the rasterizer has to process them. And even when so there used to be a thing on the CPU where we would say let's pad the buffer with dummy work. Specifically we can say here, hey, let's just push a dummy meshlet to pad the data to 32 elements, right? Which would mean that in this thread, these meshlets that we are processing just have no data in them, right? But even if you do that, I'm expecting, and see this if it's actually true. Yeah, so we are still running at like 8.8 or so milliseconds, right? So the problem is we are generating work for the mesh shader. It's almost the same problem that we have right now with our draw calls. Like we are generating empty work items for a subsequent stage in the pipeline, which is not optimal. Well, I meant to say that if I don't do this, right, then we are running at 11 milliseconds. So like right now, and this is kind of what happened before we had this check. Regardless of what you have after, like as padding for your meshlet buffer, you're just generating extra work for the mesh shader. It doesn't generate triangles because the meshlet is dummy, it has 0 triangles, but it generates work. So what I want to do is I want to say we already do a contest here, and when the meshlet has 0 elements, like when the meshlet is zeroed out, then all of these guys should be 0. And if you look at this equation carefully right now, so if this is 0, this dot product is 0. If this is 0, this is 0. If this is 0, this is 0. So if everything is 0 in the meshlet, then this equation says 0 is greater than 0. So we don't call this count. So I want to just add this like one symbol. right? And now our performance is again at 8.8 without this check. The reason why I want to get rid of this check is I want to get rid of usage of this variable as well. So what we're gonna do is let's clean this code up. This is roughly speaking how this code was, the state of this code like yesterday or something. I would still need to do something about this, but maybe I just don't. Maybe I just remove this branch for now. Or maybe, you know what, for now, yeah, like let's keep this path in like as an inefficient form. So I want to remove the mesh LOD offset usage, and I want to move this usage to the culling shader, where right now we are saying let's ask the task shader to process a number of tasks starting from 0 and then apply mesh offset later. I want to apply this mesh offset here. I think I need to divide it by 32. I'm not quite sure, but I think I do. And let me switch to release so that it starts up faster. And now we are running again quickly without the extra checks in the task shader, and it will be like the reason why this is valuable will be apparent slightly later. But this was, trust me, this was important. Let me think if I need to do anything else here or elsewhere. I think I'm happy with this for now. Oh yeah, let me check that I actually didn't break our real workload, so to speak. I'm not sure why it takes so much time to start up in debug now. I'm guessing that this code just takes a lot of time because like rand is really slow or something in debug, but whatever. So yeah, let's reduce the number of. This was a weird way to format the number. Okay, I mean, I see different meshes, so things must be working. And I think, yeah, they run at roughly the same performance. Okay, so did we start with this number? And I guess this scale, yeah, okay. Okay. This picture looks familiar. So that's that. I wanted to do this because it will simplify our LOD stuff a bit if we get to that. So yeah, so to recap, basically I sort of rolled back the thing that we did last stream where we started using mesh LOD offset in the mesh shader to call off and mesh LOD count to call off meshes that, like if you have one mesh LOD in the shader, 31 aren't used, but you still run code to process them. So instead we still are pushing dummy mesh LODs, but we have slightly tweaked the equation for the culling so that we actually discard them before they get to the mesh shader stage. So let me commit that, and then we can actually start doing indirect, draw indirect or something like optimizing the sort of culling overhead for empty meshes. So move mesh LOD offset count usage into draw cull shader. We now pad again mesh LOD buffer on C++ side. Did I like pad the right thing actually? I'm doubting myself now. Yeah, okay, all good. To simplify, to basically reduce the amount of data we need to read in various shader stages for reasons that will be apparent later. All right, so now let's go back to the Dutch rose mesh, and I guess I might as well switch to debug because I want to have validation errors. if they happen. Yeah. And let's draw a million of these guys, because why not? So here's the deal. So if we disable culling right now, so right now we are running at like 8 milliseconds of workload, and our culling takes like 0.3 or so. If we disable culling, then our GPU time shoots up to like 40 milliseconds or something like this. So we are doing culling, like culling works, right? Here's the problem though, and I already talked about this yesterday, but let's just do this again. So let's say nothing is visible, right? So there's literally like a blank screen, and we are still taking 8 milliseconds, which is like the same amount of time with this really simple mesh, right? This mesh has very, very few triangles, that we were taking when we rendered actual geometry, which suggests that the GPU is spending, and we know our culling takes like 0.3 or whatever it was milliseconds. So this suggests that the GPU is taking a whole lot of time processing these draw calls. These draw calls have 0 instances and 0 tasks, right? So regardless of which pipeline we use, there is no work. But there's a million draw calls, right, in the buffer. And even if all of them are invisible, it still takes 8 milliseconds for the GPU to process. And the thing you have to remember is, it seems surprising because we are talking about, you know, like hundreds of millions of triangles that we are pushing, and this is a measly million, and it's not even a triangle, it's a draw call. And how hard can it be for the GPU to skip a draw call? The thing you have to remember is, when you draw triangles, you're dealing with the parallel parts of the GPU, where you have like many compute units and who knows how many rasterizer cores these days and stuff like that. When you talk about command processing, you're talking about a single unit that just decodes data from the command stream. So it's not really parallel, it's basically a serial unit, and it's very unsurprising that when you push a lot of work to that unit and is expected to discard this work quickly, it doesn't do that, right? So to fix that, we will be using an extension, or like a feature. I think for the NVIDIA pipeline it doesn't need an extension, that we haven't used before, which is called draw indirect count. So this is not core valcon. This is an extension to core valcon, and it adds a function. So for the NVIDIA mesh shading pipeline, you don't need an extension. They kind of thought ahead and added this feature ahead of time. But for the interesting. Okay. For the traditional pipeline, the same problem probably applies. Let's actually check. So again, yeah, so we render nothing very inefficiently. We take basically 8 milliseconds to render nothing, and then it's the same time basically between the mesh shading pipeline and the non-mesh shading pipeline. So we need to start using this feature. What does this feature do? So right now, when we do draw indirect, whenever that happens, I'm here. We are saying, here's the number of draw calls. Please draw like a million draw calls, right? What we want to say is, please draw whatever draw calls are visible, but this number is computed by the GPU because GPU does first culling, right? So there is this function that says, instead of draw count, you will tell it the max draw count, which is kind of the worst case. I don't know off the top of my head why this value exists. But the important part is that you give it the buffer that contains the actual number, probably a 32-bit number, I'm guessing, and then offset it in this buffer where the value is stored, that the GPU will read to determine the actual number of things in that buffer, right? So we will want to use that. There's one more tweak that I might as well do now for this to work. So basically, right now, the compute shader that we have is super simple. It just reads for every source draw call, it writes a draw command that contains the information about this draw call, plus maybe visibility bit, right, like 1 or 0. What I want to do is that I want to do the same thing, but I want to only add the commands to the buffer if they're visible, and at the end of the shader we will have some sort of count, right, of all of these commands, which is not too different from whatever we already did in the task shader, but it's somewhat different. So yeah, so to do that, basically this compute shader will have to fill a portion of this buffer, so this code will become more complicated because the target index is no longer just the index of the source item, right? You have the source range of 0 to 1,000,000 numbers, and then the target range will be 0 to like 100,000 or whatever, however many are visible. And then we'll have this shader also write into another buffer, write the count of these commands. One thing that we are kind of using right now, which is why our code just worked super simply, is whenever we use draw indirect, we read the draw command, or the GPU reads the command, but also we read the index of this command, and then read the position of this data from the draw call buffer, from the draw buffer. Because we are saying, hey, one number is from 0 to 1,000,000, the other number is from 0 to 1,000,000, we'll only get calls for the items that are visible. We can't do this anymore, so because we'll have numbers, we'll have like draw call numbers from 0 to like 100,000, but then we'll have to index this array, which still has 1,000,000 items that describe the position and rotation and whatever else of the objects. So this we can't use as is anymore. Because of this, we will do the thing that we already did on stream, actually, where we will use this buffer for sort of two purposes. So let's add another integer here, which we'll call, say, draw ID. And let's replicate this in the shader somewhere. I don't know, mesh.h, yeah. Ideally, I should probably move these guys to structs. Should I do that? Let me do that. Well, actually, no, you know, whatever. So when our compute shader runs, we will just fill this, and for now, we will fill this in a dumb way. So we'll just say that this is the index. Oh, and the other thing we'll have to deal with is, it's the usual problem, our draw call count might not be divisible by 32, in which case there's like out of bounds buffer accesses here. But that's fine, we'll deal with this separately. And so then when we draw this data, we will say, hold on, okay, yeah. So we'll have to go to the shaders that read this guy. And we'll have to say, let's add yet another buffer. Let's say this is the first one, I suppose. How are we calling this? Draw commands. And then we'll have to replicate this in basically all of the other shaders. So we have the mesh shader, where it will now be, so 0 draw commands, 1 draws, 2 meshlets, and then 3 meshlet data for vertices. And then in the traditional pipeline, it will be 0 draw commands, 1 draws, and then 2 vertices. And instead of using this draw ID, we'll have to read the draw ID from the command buffer. So it will be draw commands.draw ID. And hopefully this just works. I don't know if it does. Draw commands, draw ID, and I guess same thing in the mesh shader. Draw commands, draw ID, and right now there's no difference, right? Because we are just storing the same like number here, but it will be important once we do the correct culling. And we have to change. So we have this draw indirect buffer somewhere. No, this is fine. So we basically just have to pass this extra buffer to the shader here and here, and hopefully everything works. Oh, and I guess we have to change this. Okay, so like disabling culling, enabling culling, and switching the pipelines doesn't change anything. Cool. So now we are ready to switch to the new extension, right? So let us start using this extension. It probably is a device extension. So here, khr draw indirect count extension name. I wonder if we have to say that we are gonna use that. Doesn't look like that, so I guess just we don't have to like enable feature bits or anything. And we'll have to use this function instead of the function that we use right now. And so the general idea will be there will be a buffer here that I guess it's not write only, it's sort of read write. Draw command count, right? There will just be an integer here. It will be a very small buffer. Draw command count. And then whenever there is a draw command that is visible, we will append this command to this buffer. And for now, we will do a stupid dummy thing that we will make better later. I'm just hoping that we will see this being slightly slow, which is we'll just use the atomic add draw command count. So basically, if the object is visible, we'll get the index like draw command index, let's say, by adding one to the globally visible atomic variable, right? And then we'll just fill this command, and this is where the difference between the draw index stored in this buffer and the index of the draw command comes into play, right? So if nothing is visible, this buffer will be empty. If like one element in the middle of a million large array will be visible, there will be one draw command with an index 0 that has a draw ID that's like 500,000, right? Yeah, so that's pretty much it. The only thing is, if the draw index is outside of the like range of draw calls, then things will not work. For now, let me do the same thing that we did before, which is kind of sloppy, and just pad this thing. I guess, yeah, to do so this just rounds the value up to the 32 element boundary, so that we don't have to worry about this part in the shader for now. So there's that. Now we need to create this buffer, pass it to the shader, and then actually use this buffer, right? So let's do that. That should be easy. Wherever we create the other buffers, so we'll have a buffer draw command counter buffer, and this buffer will just be 4 bytes. I actually don't know if you can create a 4-byte buffer in Valcon, but we'll try. Maybe there's some like alignment restriction or size restriction or who knows what. Is there like a special usage bit for this? I guess I don't know. I would assume that this same thing applies here. Oh, and the other thing is, something needs to initialize this value to 0. Now, you may think, yeah, let's initialize this value to 0 somewhere in the shader. I think I've seen some sample do something like, if we are processing the first draw call ever, let's like assign this guy or something like this. As far as I know, this does not work correctly because there's no real ordering between shader invocations that is defined by anything. So what you have to do is you have to 0 initialize this value before we start the compute shader. Now we could write another compute shader for this, but I think we might as well do use the buffer fill operation, which I'm assuming should work just as well. So we are creating the buffer with 4 bytes. It will just contain the counter. And also this time we will not forget to destroy it here. Then we'll have to change this code, but first let's like change the code that actually produces this value. We will 0 initialize this by calling cmd fill buffer dccb buffer offset 0 size 4 data 0, right? And then we need a barrier. Let's call this call barrier, and let's call this fill barrier. We need a barrier that says we were writing to this buffer. I don't think this is important. From a transfer operation using a... No, wait, this was important, right? We were using the transfer write operation previously, and now we will start using this shader, and it's really shader read or shader write because we are doing an atomic add, and I'm assuming that this implies both reads and writes, right? And we were doing the write from the pipeline stage transfer, and now we are doing compute. Yeah, it might be slightly more efficient to initialize it with the compute shader, but we are doing this once per frame, so I'm assuming it doesn't truly matter, and it might actually be more efficient this way. I don't really know. But so now we are setting this value to 0. Then we are waiting for this write to complete before the shader reads or writes start on the compute stage. Then we are running our compute workload that uses this buffer, right? And then updates this buffer and does whatever. And then finally, here and here, we need to start using this buffer. So instead of this, we need to use this extension, draw index indirect count. There is an AMD version as well, but this is just an earlier version of this extension, because AMD shipped this extension first, and then it got sort of promoted, I think, to the to be a standard. So instead of this, we need to specify the buffer offset 0, and then our maximum draw count is still the original number of draw calls, so like 1,000,000. And yeah, that should be it. And here, I think NVIDIA should have a variant of their thing as well. Let's see. Yes, there's this indirect count. It's basically same deal. Add DCCB buffer 0. Yeah. Maybe that's it. Let's see if this works or if it explodes in some crazy manner. Okay, so our culling is pretty fast. I was hoping that this will be slow and we'll have to optimize it, but maybe we won't have to. So now it takes 6 milliseconds, not 8 milliseconds that it used to render things. If hypothetically, you know, nothing was visible, then we would take 0.3 milliseconds or so per frame, and this is just culling, right? So if nothing is visible, we are now really efficient. If things are visible and some other things aren't, we are more efficient than we used to be. We used to take like 8 milliseconds, and now we take like 6 milliseconds or something like that. Oh, and in a traditional pipeline, we might be faster because mesh shaders, for right now, our implementation seems to be slower when the objects are super simple. Let's see if that's true. Yeah, so in traditional pipeline we are way more efficient. We are like 3 milliseconds, and mesh and task shaders take like 6.4. I don't quite know why that is. I suspect maybe if we didn't use task shaders here. Oh, that's actually, is it easy for us to try? Is it easy for us to try? It might be. There might be other reasons why. Let me commit this code. Well, I wanted to make, yeah. So the thing is, this is not a very efficient thing to do because we are doing the global atomic access for each draw call. I was hoping that this wouldn't be very fast when we do culling, but I guess maybe it's not very, maybe it's like fast, but maybe it could be faster. So I guess let's try this anyway. Let me first switch to release because I kind of want the thing to start faster, and then let me enable vsync or disable vsync, whichever direction the vsync goes, so that we have stable metrics. Oh wow, wait, no. Okay, so we are taking like 5 milliseconds, roughly speaking, with the mesh LED mesh shading path, and 0.23 to cull. And then, yeah, we are losing efficiency with the mesh shading path substantially on these really small meshes, right? It might be because we could be more aggressive on, like, on these parameters, but this is hard. It's hard to be aggressive on these parameters because we are using like one draw call, right? So that might be painful to do. Maybe this is the point where we are actually losing time on having the task shader even enabled. So we can check if that is true. Sorta. But I guess this is the point where I want to submit first and then figure things out later. So let me check. There's the scale over 2, but that's fine, we'll clean this later. Clean this up later. Nah, I guess I might as well try the more optimal way to do culling first, and then we can clean up the code and submit. So yeah, so 5 milliseconds render time, 0.23. Faster with traditional pipeline. Let's quickly try to disable the use of the task shader, and we'll lose cone culling, but cone culling isn't working here anyway. Oh, but then this modification will be kind of destructive. I'll try this later after we submit the code. So yeah, so here's the thing. This global atomic, we are doing this for every object that is visible. Now, in theory, NVIDIA's shader compiler can optimize this. I don't know if it does. We don't have a way to know. So if it does optimize this already, then the code that we will write ourselves right now will be like useless in the sense that we'll just make the code more complex, but will not actually make anything faster. But we already have learned this trick when we were optimizing the task shaders, where you can use ballad, and if you enable a magical extension, okay. So here's what you can do. You can say there's 32 threads here. They compute visibility bit, right? Then we can aggregate the visibility bit from all 32 threads into a bit mask. Then for each thread we can ask, can you add up everything except for myself in that bit mask, which will give you the index that you need to write, and give me the count of all things that we need to write. Then let's add, and I guess if count is 0, then we can just return from the shader, because this means all threads in our warp just didn't find anything that's visible. So let's do an early return like this, right? So then if there is something, if there's at least one object that is visible, then let's do one atomic operation in the first thread. And I guess I need to do the, do I need to do some barrier thingy again? I did this, but we removed that stuff. Yeah, so here I don't need this. I'm wondering if I need to do some barrier again. Because it's like in some other threads, I will be using the value. Oh, I need to broadcast this. Hold on. So in thread number 0, we will reserve the space for all visible items. Then in any thread, really, I want to get the value of this index, but this value is only available in the first thread. So I need to use some other wave operation. Let's do this subgroup ops tutorial. I forget which one it is. Basically, I want to ask in each thread, hey, can you give me the value that is that index in the thread number 0? Broadcast, I believe. I basically can use broadcast first. No, broadcast is the lowest active. I basically need broadcast 0, I believe. Broadcast the value to all other invocations. I mean, I don't need an if there, so I can just do DCI equals subgroup broadcast first DCI. So this propagates the value that we have computed in one thread to all other threads. And then if the thing is visible, then I can write this like this. And I guess it might be nicer to do it like this. Hold on, so draw call index group, let's say, or draw call group index, and then draw call index is broadcast draw call group index plus index, which is this guy. And I guess I could move this here. Alright, so I think this works. Don't quote me on that, let me see. Alright, it seems to work. Unfortunately, our GPU time for culling didn't improve. But this may be because NVIDIA's compiler is already doing this optimization for us. But so when before we did an atomic add for each thread in the warp, now we are explicitly saying that we will do an atomic add once per warp, only from thread 0, if anything needed to be added. So say if 16 threads in the warp said that visible is true, then count will be 16. We'll allocate space for 16 draw calls, propagate this value from thread 0 that did the add to all other threads, and then do the addition, right? Yeah. So that should be more optimal. We don't see a performance difference. It could be that doing a lot of atomic adds isn't that big of a deal on NVIDIA, as long as you're doing this to the same location for some reason. That would be odd. It could be that the driver is automatically doing this optimization for us. But whatever the case may be, this code should be fast in all cases. And I think again we are playing a bit fast and loose with this 32 value because we are assuming that the subgroup size is 32. So this code might not actually work on Intel, and that would be unfortunate. So maybe we don't, maybe let's do it like this. I will add a thing here, which is like ballad, let's say 0. And for now, I will keep this code here, but I will if-def it out. Because the other stuff that we were doing when in Task Shader, where we were hand waving around, you know, yeah, the value, the number of the subgroups is 32, it's all good. This code was NVIDIA only anyway. This code works on all architectures because it works for a traditional rasterization path as well. And it's not that hard, just need like a loop around something somewhere here, but I don't want to do that right now. So let's just say that if ballad will do this, and then here if not ballad, we'll do UNDCI atomic add, draw command count 1. Like in theory, it's not very hard for the driver to optimize this into the exact same code that we have written here. I just don't know if it does, right? If it does do that, then this is awesome because we don't need to work hard to get the same result. If it doesn't, then we might have to work hard. And then I'll leave a comment here that says the ballad code assumes that GLX subgroup size, I think, or whatever it's called, is 32, which needs to be revised for non-NVIDIA architectures, right? Okay. So let's check that this still works. And so we have optimized the culling. Now, when objects aren't visible, they don't generate work for the rasterizer, which is nice. We should make sure that we can scale to larger numbers of things. Oh, and now let's actually get back to the old sort of scene that we were using with this 4 meshes and 50,000 draw calls. We still need that. And remove the scale. And that's probably it. Okay. And I guess disable vsync. I mean enable vsync. Okay. Yeah, so there is this, oh, I didn't check if the, yeah, like mesh shading stuff. At some point, I guess we may need to investigate what's going on with the performance Like when we render complicated meshes, mesh shading is substantially faster, like twice as fast in this case, right? More than twice as fast. When we render really simple meshes that are like less than 100 triangles or whatever it is, then mesh shading is substantially slower, again up to 2x, right? Which might be because we have this task shader overhead, or might be because the size of the primitive groups, etc., in the mesh shader are sort of optimized for really large meshes. So maybe if we are more conservative there, then we can have a better balance, or maybe it's something else. But this is good enough for now. So in here we are pushing some number of triangles with culling, and the culling is now more efficient because it doesn't generate extra work for the command processor when it's not necessary. So let's commit this, day 12. Use draw indirect count to optimize culling. It's not really culling, but like culling doesn't run faster, but the, I guess, command processing instead of, oh, and we now don't need, okay, hold on, yeah, I'll finish typing this. Instead of generating dummy draw calls, we now only write draw calls that we need to the output buffer. Substantially reduces overhead of command processing due to lack of empty draws. So yeah, I forgot to remove, now that we have an if here, we don't really need an if here. So we can remove that, and we can remove that, right? And that works, and that works, and that works, and everything works. So let's fix that. Okay, cool. So we're done with that. And our next frontier is level of detail. Let me look at chat and see if anything is going on there. No. Nothing in chat. If anybody has any questions, as usual, feel free to ask them. Because if you don't ask the questions, there will be no answers to the questions. Why does YouTube... Oh, there's a notification. Okay, never mind. Okay, so draw indirect count seems to work. Let's just double check that we... with some of these newer features, I sometimes discover bugs where it's like validation errors should have triggered an error but didn't. So I filed a few of these. Some of these have been fixed already. Some of these, I think for this there's a pull request. I think for this there might not be a pull request yet. So I want to just double check that we did everything that we needed to be doing, because validation errors are silent, but I just want to double check. So we did that. Yeah, there's this feature which is somewhat annoying. I'm not sure what it is on NVIDIA. Let's check. But I think the standard says that the minimum value, the minimum maximum value of this feature, like the guaranteed number of things that you can render with one draw call with this, is like 65,000, which isn't unreasonable. But we have been trying to do like 1 million and it all worked. So I'm assuming NVIDIA's limit is much higher, but I don't actually know if that's true. We don't even... Oh yeah, so props limits is the thing. Okay, so NVIDIA is very nice. NVIDIA says you can draw up to 4 billion draw calls. We don't care. This is nice. Thank you, NVIDIA. We don't have to worry about this. It might be that like on Intel or something, this value is lower. Like you can deal with these limitations. So basically, the minimum limit, like let's assume that the maximum number of draw calls that one command like this can draw is 65,000. What you do then is in the counter buffer, instead of one integer, you store like 256 of them. And then instead of the compute shader running like once, you'll just run it for each. Basically, yeah, I think what I would do is I would run the compute shader for each chunk of the source draw calls that has 64k elements. And then for each chunk, I will run the compute shader and then ask it to write to a buffer. And then I'll still need the shared, I still need the shared atomic. It becomes a bit painful because you kind of want a single contiguous range, but you don't want to necessarily. I guess if you have memory for the worst case, then it doesn't matter. Yeah, so that's fine. So basically for each 64k range, you call into a separate range in the output buffer, and then you use a separate count, and then you just have a for loop on the C side that loops some number of times, and then if you have like say 256 counters in this buffer, and up to 256 groups, then your limit of the draw call count is 16 million per frame, which seems plenty, right? And then if you need more, you can use more than 256 counters. So it's not very hard to work around this limit, but it's somewhat annoying to work around this limit, and it looks like here we don't have to, so that is nice. I don't know how it works on Intel GPUs. Let's see. Is it possible to push commits immediately with commit? I mean, it is possible. If you're asking me to do that, I mean, I could do that. It doesn't matter to me at all. So on Intel, the limit is also basically, let's call it very large. Interesting. Okay. What about AMD? Let's find a vendor who we don't like. That we don't like. Like there must be some vendor, since the spec says that. I think max draw indirect. Let's find this. Yeah, so the worst case value for this feature when it is supported is 65,000. So who was that? Cannot be AMD. There is no way. Not AMD. So all desktop vendors support basically unlimited unlimited numbers. The problem is a lot of mobile vendors may not support this feature at all yet, but let's see. I don't know. So like Qualcomm supports a lot. Is it ARM? So this is Android 7.1. I don't want to look at that. Drivers are too early. So this is Android 8.0. Okay. So ARM doesn't support this feature at all yet. Interesting. Okay, there's also PowerVR. I guess it should be Image Tech. No? But okay, some vendor decided that they don't support. So let's look at these. These are pretty late drivers. And this is 2 billion. So ARM doesn't seem to support this feature at all. At least in like these drivers. And that GPU. Every other vendor that I know of supports way more than 65K. Okay, I don't know why the limit is so low, but oops. But regardless, it doesn't seem like we should care, right? All vendors, even on mobile, that support this feature support way more than 65K. All right. So now let's start working on LOD. Before we start working on LOD, we will split, remove the space or the white space line. We will split the structures a bit more. I talked about the fact that I might want to do this last time, and this time is the time to do it. So what do we want for LODs? For LODs, we will use the algorithm, the simplification algorithm that's available in my mesh optimizer library that we're already using. What it does is it generates a new index buffer for each LOD. So we'll have to generate a new index buffer and a new sort of meshlet buffer for each level of detail. So we'll have to use something like, let's say we have up to 8 level of details. So we have up to 8 of everything. And then we have some sort of, let's call it LOD distances, some sort of data that tells us when to switch levels of detail, right? The thing is, right now we are lazily storing all of this stuff in the draw call, and this is getting large, right? So this is like 1, 2, 3, 4, 5 times 8, 40 times 460. So this is 160 bytes of data for the mesh sort of definition, right? Compared to the actual draw call count, it's like super small. When you use a million draw calls, 160 bytes per draw call translates to 160 megabytes of data for draw calls, which is not fun, right? So instead, what I want is I want to use just something like mesh index, right, and put all of this data away into separate struct. Now, the reason why we have moved meshlet offset out is I don't want to really access this data when we draw the meshes, because we don't truly need it, and like it's better if we don't. So what I want is I want to still keep the vertex offset here, because vertex offset is now the only variable that the mesh shader or task shader stuff uses out of this. So for these variables, basically what's going on is this is used in the mesh shader, and this is also used in our culling shader. This is used in our culling shader only. This is used now in our culling shader only. So I will keep this vertex offset here for, it's slightly redundant because it's like, it's just determined by the mesh, but this is the thing that will not differ between LOD levels. And it will be easier and faster to access it if it's just here. So I want to change the data layout to that. And I want to move this to a struct, let's call it mesh. And then we'll just move these guys into a separate buffer, right? And then we can expand the size of the structure without worrying about the draw call size. Yeah. So let's do that. And then the other thing that we'll do, that I wanted to do anyway, well, no, that's fine. That's the only thing. Yeah, so some of our shaders won't compile anymore. Specifically, the draw, like the draw color shader, will not compile. So what we will do is here, in addition to the draw buffer, we'll add the mesh buffer. Let's call it meshes. Meshes 1, 2, 3. And then instead of using, yeah, we basically, if the draw call is visible, then we will just load the mesh from the meshes buffer using the index, right? And then all of these counts just will come from the mesh. Yeah, so this value is now duplicated here. So this is equal to meshes mesh index vertex offset. Helps essentially data locality in task in mesh shader. I just don't want to read this buffer even at all from the mesh shader. It's just redundant and from any other shaders. So I just want to copy this here. So we already have this mesh structure. Let's see if we closely mirrored it. Well, oh, nice. Right, this can also go and should go here, right? And now we need to align this by 16 bytes. So let's restructure this so that it's the same data. And we can even do count, it doesn't really matter, vertex offset, vertex count, index offset, index count, mesh let offset. So now this is the same struct, right? And yeah, so now we don't need these. This was the local space bounding sphere, and we don't need this anymore here. So this is 16 more bytes that we don't need out of our draw call structure. So now our draw call structure, which we also now need, oh, this was aligned, cool. And yeah, we'll need to change this data here. But now this is 1, 2, 3, so 48 bytes, right? So this is good. We have a lot of space here. It might be reasonable to target something like 64 bytes for the draw call data, or 48 is fine, because really the thing that we'll want to add here will be material index at some point, and maybe something else, but there's a lot of space here for future expansion. So let's change our data layout to match. We don't need this here anymore, and we don't need any of this. We basically just need the mesh index, and we don't need that. And I forget which one was first. Okay. So this is correct. So we already have this vector that we're already filling. We just need to upload these, right? And yeah, as the to-do comment says, all of this is just a mirror of the GPU data, and we might rework the way data is uploaded, but not today. Because I want to get to LODs. Let's restructure this so that we fill data in the same order that it's declared in. So we want a buffer with this stuff. I want to call it mesh buffer, but we already have meshlet buffer. So let's rename meshlet buffer to MLB. All right. And then we want a mesh buffer. I don't know what the order of any of these things is. And a lot of these buffers don't have to be that large. In fact, yeah. Like now we are burning a lot of GPU memory on like a bunch of 128 meg buffers, where some of these are larger than others. So the mesh LOD buffer is relatively small, the mesh buffer is tiny, the mesh LOD buffer is relatively small, mesh data buffer and the index buffer are relatively large, the vertex buffer is kinda large, right? I think this is the rough order. So we don't really need to use like 128 megs for all of these, but this ties into the fact that we also don't need the copy of this data on the CPU, which we have in the vector right now, so we'll have to rework this later. Okay, so now our culling shader uses the mesh, yeah, so this is now like 0, yeah, so draw calls mesh is draw commands, draw command count. And we need to change the way how we fill this, so we don't need to copy this in any way, right? The only thing we really need to copy is we need to copy the vertex offset. So let's do that, or I guess let's do this. Don't need this, and then that, and then in this shader I guess we need to, like, since we now need the center to read the center from the mesh, we need to do it like that. And this code is now easier to read because it's more obvious where sort of things are. Like this is the mesh center, not the draw call transformed center. Stuff like that. Let's see if this works or if I forgot anything again. Hey, seems to work. Alright, so I want to commit this as well because move mesh data into a separate structure buffer, and this will help us add data for LOD without like inflating the size of the draw call buffer. Alright, so now let's try to add level of detail support. Hopefully it will not be that hard. Oh, I wanted to move this out into a separate function again, because what we'll be doing now is we'll be adding a LOD code here, and this function is getting long. And we merge this. It's weird how today on stream we are undoing several decisions that were kind of bad in retrospect from last stream, but this is actually sort of par for the course, like this is completely normal. And healthy, I would argue. Like you make some changes, you don't worry too much about whether they will be future-proof. You treat code as disposable, so that it's super easy for you to rework it later. All right. Okay. Oh, now the function and oh. Okay. All right. So the way this simplifier works is you can call a function called mesh opt simplify that can produce an index buffer, which is the destination argument, given an index buffer from the sort of previous level of detail, let's say, the positions, and it needs to know how many triangles you want, or indices rather, and how large the error should be. The error metric isn't particularly well tuned, so this is more of a sort of stopgap, like use this to make sure your buffer doesn't get too deformed or something like this, as opposed to being correlated precisely with some sort of visible error on the mesh, right? So oh, that's actually an interesting question. I will cover this in a second. So basically we just need to call this function like a bunch of times and generate progressively simpler versions of the mesh, and then store them as in the index buffer, right? Like the same way how we were doing things here. And then also generate meshlet data for these, because the meshlet data depends on the index buffer mostly. And then in runtime we'll have many different index buffers available, one for each LOD, and then we can pick one based on the distance, and then hopefully we will render roughly the same scene with way fewer triangles, and that will be amazing and awesome. So let's start to do that. There was an interesting question, am I using ECS? ECS stands for Entity Component System. I'm not really using ECS, but maybe one reason why maybe you asked, which I felt was interesting, is if you notice the way how we work with the data here, we have a bunch of structs, and we have large arrays for all of these structs that are directly reflected into the shader. And some of the structs reference other structs. So like this struct references the draw ID, which is in this array, right? This guy references the index, which is in this array. This guy references meshlet data, which is in this array. This guy references meshlet data, which is in some other array somewhere else. And also the indices somewhere, like I guess from this guy, reference the vertex buffer, right? So you can think of this as the data-oriented design that is loosely, it's not truly related to ACS at all, but some people think that these are really close together, which they aren't truly, but it definitely reminds, like ECS reminds you of data-oriented design, or data-oriented design may remind you of ECS, and what we are doing right now is definitely reminiscent of that, because this is like the most efficient way to do memory layout in a lot of cases, and it's the simplest way for sure. GPUs don't have pointers, so on GPUs you kind of have to communicate data using large buffers of structs and indices. And it's pretty easy to do this, right? We were like reworking all of this without really skipping a beat. It's not hard to write this code. Anyway, so I was saying, so we need to start calling this code. Let me, so there is the vertex buffer, and then for each level of detail, we'll need this. This code runs once. This code doesn't run once. So let us first add space for all of these things. So let's see. So we need mesh let offset and count. I guess I could do this, where I just move this data here, and then I do this. Let's say there's up to 8. And then I want some sort of distances, so I guess let's do this. And then let's mirror this on the C++ side. Here. So again, each level of detail is just an index buffer in my algorithm. It does not generate new vertices, which is actually convenient in this case, because yeah, we just do that. We may want to store the count of levels of detail, but we also could say that everything has up to 8. Like, and then we just pad the data with stuff. It doesn't really matter. I guess we might as well store some sort of LOD count. Yeah, I feel like next weekend we'll try to share these structures between CPU and shader code, because I have to be super careful and maintain them like one-to-one. And then there's 4 bytes of padding here, which is weird, because then this guy is not aligned to 16 bytes. Probably doesn't matter. So yeah, that's that. So let's do this. And just make the code compile. And I'm not sure what the specific semantics of the distances will be, so we'll leave that as this for now. And then basically here we want to ask what's our LOD index, and for now it's just 0. And I don't know if compiler will actually carefully optimize all of that, but let's assume it will. Right. Okay. This triangle count makes no sense anyway, but fine. We will fix this later. I don't know if we'll have time. If LOD stuff just works, then we will have time to fix that. If LOD stuff doesn't work, then we won't. So here's what we're gonna do. Let's just say, do we need this vertex offset? I guess we do. Yeah, I want to restructure this code a bit so that, I guess, let's just start filling the mesh here. Some mesh vertex offset, and then this will be in a loop. This can go here. And then that. right. Okay, so now let's fill LOD data. So what we will do is we will have can I do this in place? I sort of forgot if I can. I think I should be able to. Yeah, okay. So yeah, okay. So let's do like an LOD index, let's say, and then while LOD index is less than array size mesh LOD LODs, we will do the following. So first we will write the current data, and I want to copy, just for clarity, LOD, why am I, okay, yes, LOD, I guess let's do LOD count. I guess let's just do this, mesh LOD count. So we will be modifying this vector in our loop. So in each loop iteration, we'll add our current index buffer as a level of detail. So we are computing index offset, and we might as well just write this directly to the mesh index mesh LODs of okay. And I guess we could do this, yeah. All right. Oops, wait. Okay. So then, so we are filling the index data, then we're adding the current LOD. And then this code unfortunately has to stay here. Yeah, okay. And then we are adding meshlets using the LOD index buffer for our current LOD. And again, this can be just that. So this is these lines. These lines we don't need anymore. So we still need to compute LOD distances somehow. I don't really know how. I mean, this will just be something super approximate. At the end, we'll say something like so ideally you would look at like the mesh complexity or something. I'm wondering, do we even need this here? Do we even need this in the data? Maybe not. Let's, for now we don't really have an error metric or anything, right? So we might as well just compute this in the shader somehow, and then we can figure it out later. Yeah. So yeah, just ignore all the distances for now. So we have added the current level of detail, and then we wanna generate the next one. So what we will do is this. If mesh LOD count is still less than array size mesh LODs, then we'll try to simplify the current index buffer into itself. Next, say indices. So we'll say, okay, LOD indices data, same thing. LOD indices size, vertices vx, vertices size of vertex. Then we'll say how many indices do we want to have. Target. We'll come back to this. And then we'll say what our sort of error bound is, and let's just say for now like 1 in -4. This is just a sort of fuzzy metric that says that stops the simplifier before the mesh is too significantly destroyed, I suppose. 1 in -4 or 3 is not too bad. So for now, I want to say that each level of detail will, like the next level of detail should be, let's say, 75% of the previous one. So let's do that like this. Okay. And then in some cases the simplifier will say I'm stuck. I've looked at your mesh and I can't really simplify anything. Or I looked at your mesh and you asked me to simplify to 75%, but I kinda like can't really get there. It basically will say I'm stuck, like because the error bound is just too large. So if next indices is the same, it should be that next indices is less than or equal than the index count we started with. And if it's the same, then we will break from the loop, because this means that we've reached the error bound. And otherwise we'll just resize the buffer. But then the other important thing that we need to do is we need to do this optimization. The reason why I structured the loop in such a weird way is because I didn't want to treat the level of detail 0 in a special way, but I kind of have to, because here we are optimizing each level of detail, the first level of detail for the vertex reuse cache and then for the vertex fetch cache. But this changes the vertex order, and when you do so for one LOD, or other LODs become invalid because they're all sharing the same vertex data. So basically from this point we cannot modify the vertex data anymore. So I have to do this, but I can't do the other thing. So yeah, this is LOD indices size. And that might be it. I mean, we still aren't using these, obviously, but let's see if this even works in any reasonable fashion. So now our startup takes a few seconds in debug, because in addition to everything that we have been doing before, we also have to like generate all of that and optimize that and like simplify and stuff. And some of this code isn't super optimal in debug. In Visual Studio, at least, I'm planning to look at this later. But okay, let us switch to release so that we don't have to wait for a few seconds. Right. So in theory, I guess we should have looked at the actual data that we are generating. Let's look at the data that we are generating for one of these meshes. So we generated 8 LODs. The first LOD has 86,000 indices, divide by 3 to get triangle count. And then we generate a bunch more stuff, and then the last one has like 3,000 triangles or so. We can be more aggressive, we can shrink more aggressively for each LOD, but this seems okay to me. Okay. 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 Okay, okay, cool. Now, let's use this data. So yeah, so instead of doing this LOD indices stuff, let's just have some like formula here that says, for now, do something super simple. let's compute the distance between the center of the bounding box, which is center, and the camera position, which right now is just 0. And then let's subtract the radius, so that if you're within the radius of the mesh, we treat it as if you're on the border of the mesh, so that things don't change in like too weird of a way. And then do max with 0 to clamp this to 0. And then let's take this value, and then let's say that we will switch the level of detail in like 2x distance increments. So let's do a log of LOD distance to get the maybe I want to first subtract something else. Hold on, let me think. Oh yeah, I want to divide, right? Then I want to divide, I guess, by like something, by 10, say. I'm not sure what our distances are, what units our distances are in. Hold on, let me look at this. So 50. Okay, so we'll want to increase the range, but for now let's not even divide by anything. Let's be super aggressive. So let's just do. Oh, hold on. I want this value to basically like start at 0, so I guess let me start at 1. And then I want to do log 2, which will make it start at 0. And then I just want to cast this to an int, but I want to clamp this, so between 0 and mesh LOD count -1. And I guess I want to cast to uint. Well, yeah, I guess that's sort of what I want. Oh, it's not length, sorry, it's distance. Yeah, okay. It will be hard to figure out if it works, but now let's switch to release. And let's pass some extra variable here that will allow us to like disable the LOD selection. I don't know how to pass it. Let's just do this, I guess. Oh yeah, we can do this, and then we can do this, right? Are booleans 1 byte in GLSL? Can you even store booleans in uniform blocks? You can. Are they 1 byte or 4 bytes? Let me use ints just to be safe. So yeah. That. And also and that. Somewhere, doesn't matter where, I want one more struct, which will be like draw call data, 6 frustum planes, and culling enabled and LOD enabled. And let's set a boolean that we will switch as usual on the key press. Alright, and let's also print out the value of this. Okay. Oh, well, yeah, I see. I also should figure out how to make it so that when I double click the error, it just goes like where I want it to go. Frustum and declare that. Oh, yes. Okay. Okay, so when I switch LOD, I'm not sure how visible this is on stream, but when I switch LOD, and right now I think, I'm not sure how aggressive the switch is, because I'll need to think about my beautiful log math, but we are substantially improving the performance, so we are going from 10 milliseconds when it's disabled to like 3 milliseconds when it's enabled, right? You do see a bit of a difference when I switch, at least I do. I don't know how it reflects on the stream. It's not very apparent. It's like apparent when you switch because the edges are different, but it's not actually very visible. And I don't know how aggressive this really is because I'll need to do the math. But this works, I think. Let's try to make it more aggressive. How do I make it more aggressive? I guess I have to like divide my logarithm by something to make it more aggressive. Because right now we are saying that it's actually pretty aggressive right now. Right now it's saying that it starts really aggressive. It starts by saying so we have a draw distance of like 100 or whatever it was, but we are only generating meshes in plus or minus 50. Yeah. So at 50 units away from the camera, the distance will be 50, and then the radius, let's just say it's 0. So this will be 50. And then we'll do a logarithm of 50, which will be like 5.5 or something like this, 5.4, 5.5, and then we'll switch to the level of detail 5, roughly speaking. So we probably aren't even using the last like 3 LODs or whatever it was, but it's relatively aggressive close to the camera. Ideally, you would have something where you would say at distance like up to a distance, say like 10 or whatever your units are, right? Our units right now really strange, but like let's say it's 10, you have LOD level 0, and then 10 to let's say 20 it's the next one, and then let's say 20 to 40 it's the next one, etc. For this, basically all you need, I think, is you need to divide something. You need to divide this distance minus, I don't even know if minus radius at this point is important. Might not be. Might not be. I just wanted the thing where if the object is large, we don't switch the same way as if the object is small. But maybe I should have divided the distance by radius. I don't know. You can kind of do whatever. It's like it'll take tuning on more. We can't really move the camera, right? So it'll take tuning on a more comprehensive sort of test. But let's make it more aggressive. Let's divide this thing by 5. And I don't even need to clamp this, I suppose, because logarithm of 0 probably is defined as negative infinity. Well, I don't know how this will work out. Yeah, I want to keep this as is for now. Wait, I thought I made it more aggressive. Oh no, you have to multiply to make it more aggressive. Never mind. So I mean, yeah, that's definitely, there's more stuff changing, and also we are running faster than, yeah, than we were before. So maybe we want it to be that, but that way you can see even the closest mesh, it changing the LOD level. But it's pretty highly tessellated, so it's not as apparent. But okay, for now, let's just keep this as is. And then we can increase the range of our scene. Let's just increase it to 1000, just to see what happens. And our draw distance probably should also be 1000 or something. Or actually, let's keep the 100 for a second. Yeah, but now we need way more objects to fill the space, right? So let's go back to this million that we started with. Let's see how that works. That isn't even utilizing the GPU, it's like 0.8. So let's draw 10 million meshes. I don't know, I don't care. Well, our draw distance right now, our draw distance cutoff is pretty small. Oh wow, it takes a lot of time to start up now. Why does it take a lot of time to start up? Oh, we might not be fitting into the buffers now. Because 10 by, yeah, we only have a 128 meg buffer for some of this stuff, and it's just not enough. Okay, you know what, let's keep a million for now. Let's make this slightly less aggressive. Let's just make a variable here, like float scene radius is 500, and then draw distance, let's move here. So, I mean, this is relatively reasonable. Yeah, so we are running like 3 times faster or something with LOD on, and in this scene, it's really hard to see the switch. Some pixels change somewhere in the distance, but it's not very obvious, right? We can increase the draw distance because some objects are cut off right now. Oh, okay. A lot of objects were cut off apparently. Whoa. Yeah. Okay. Hold on. Like for a setup like this, we might want to be more aggressive with our LOD thresholds. So let's just say that aggressively each level drops the count by 5. Oh, by half. But then objects in the distance seem to decimate to nothing. Like there's a substantial difference in volume really far away, right? Yeah. So let's keep the 0.75. I just want to tune this to the point where we have good performance, but it's not too crazy. Like you can sort of understand what's going on screen. Maybe I want to reduce the field of view actually, because 70 is relatively, well, it's not too wide. Assuming we divide it by 5, it's kind of wide, but it's, I guess, typical in games. I don't know. Yeah, this is a bit more. I might want to leave it like this. Alright, so we are running at like 15, so we're running at 60 FPS, We don't know how many triangles we are pushing right now. The 856 million is not true. Also, I think this actually overflowed, but this is not true. And the 63 million draws per second is also technically not true. We have a million objects and we are rendering at 60 FPS, but a lot of these objects are culled. If we disabled culling, it would not run at 60. Yeah, if we disabled culling, it would run very slow. But this is pretty reasonable as far as... I'm just worried that also in debug it will take a while now to start up. So maybe for debug we'll have different settings at some point. And maybe we wanna not draw the entirety of the scene. Yeah, so this I think is good, right? So we're rendering at like 6 milliseconds per frame, which is super comfortable. We aren't rendering some objects that are in front of us. Ideally, you would see fog or something like that. And you see that there's a lot of stuff on screen. And level of detail improves performance like 4 times, roughly speaking. Which is what we wanted. And then culling, if you disable it, things are super slow. And then if you disable both level of detail and culling, then things are super slow. But okay, so this is pretty good. I am happy with that. That just worked. Now I want to add the counters. Let me look at chat. Chat has nothing so far. So yeah, this was cool. Now ideally we would also have some way to actually fly through this, and because right now you can see the LOD switch on the sort of entire scene, but it's harder to gauge how well the LOD works because you can't like fly through the scene and see objects pop. So yeah, and obviously the level of distance switch metric will need a lot of work. I'm sure it doesn't really work very well. We'll have to think about how it should behave. But this is not too bad. This is not too bad. I like this. And I'm not actually sure with the current metric whether we are drawing any objects at full resolution close, because it looks like the object here is slightly changing as well on the leg. The shading changes a bit. This object doesn't, so this leg doesn't change. This does change, and this does change, and this does change. So it looks like we may be only using the LOD 0 like really close to the camera, which is not necessarily optimal. But this is just the LOD curve. Like maybe you don't want the maybe you want the level, the first level to switch farther away from the camera, but instead of logarithm 2 on the distance, you want to have logarithm like 1.5 on the distance, because that's kind of how we are generating levels of detail. But again, without a real camera and the scene that's less chaotic than just like a crazy amount of objects like randomly scattered throughout in 3D space, it's really hard to tune this stuff well. Oh, now that we have added the final thing before counting the triangles, now that we have added this struct that I used to control the enablement of these things, let me just add draw count here and remove the to do comment. So the only reason why we needed this padding was that when this compute shader runs, we run it on more objects than we had. So like we run it on, if you had like 5 objects, we still run it on 32, and we could be reading data that's just outside of bounds or something. So I guess I want to wrap this entire thing into an if. Or I just can say that I want an early return here. And that should fix that particular problem. A million is technically divisible by 32, probably. Is it? Yeah, it's to the power of 6, and that's to the power of 5. So it didn't really change anything for the million, but that's sort of nicer. Yeah, I definitely should fix rounding here, but okay. And so far we have few shaders, so it doesn't take too much time for us to compile them, so we don't really need a cache, but okay. So let's commit this now. I feel like I might later add, maybe like next week or something, or maybe off stream, we'll see, add some if def so that, say, in debug we have fewer objects so that it starts up faster. Or maybe like on Intel GPUs we need fewer objects because there is no way an Intel GPU can render this craziness at like real-time frame rates. D12 and LOD support. We are currently generating 8, well 0 through 7, right, levels of detail, with each successive level having 1.5x fewer triangles. Our LOD switching curve is 2 to the power of distance, or like log 2 of distance, which is the same thing, right? So let's just say it's log 2 of distance, which is probably not optimal, but we can deal with this later, right? I don't want to deal with this now. And yeah, this substantially improves our performance because we are balancing the number of triangles that we are outputting better. Okay, so that's basically it. That's basically all I had. I want to quickly see if I can implement the triangle counting that is more precise. And then I'll answer questions if any, and then we'll end the stream, right? But yeah, this has been good. So we are feeding like 1 million objects right now to the GPU. We are calling a lot of them away, especially since we made the field of view a bit narrower. So it's right now like 50 degrees, which is what, like 1/7 roughly of the 360. So we are calling a lot of objects away. But then we are applying level of distance on all of them that remain, and then we have lots of objects on screen. And level of distance is not too apparent when I toggle between it on and off. You don't see, these objects are pretty high poly to begin with, so that makes sense. But this is pretty good. And yeah, when level of detail is enabled, we run at like 6 milliseconds per frame. And probably with vsync on, rather off, we'd run even faster. So that's good. And it takes us like 0.14 milliseconds, right, on the GPU to do culling, which is nothing compared to the rest of the frame. So we don't really have to worry about any higher order like acceleration structures so far. All right. So yeah, triangle counts. So there's kind of two ways to do that. So one way to do that is to just ask the compute shader that does draw culling to add more things to this buffer. So like right now this has draw command count. Maybe it should also have some stats that say the number of vertices, or not vertices, triangles. And then we could read this data on the CPU side, but that requires copying this buffer somewhere. So that's not super awesome. The other option is to use the pipeline queries. Let's see. Like, yeah, pipeline statistics query. Which I guess I want to try. I never used this in Valcon, but I used it in DX11. The only problem with this one is this cannot give us the number of objects that are visible, because it doesn't count draw calls, it only counts like everything else. So that is not great. So we kind of have like, we would like to, yeah, I would like to read this buffer on the CPU anyhow. But the problem is to read this buffer on the CPU, we should either just allocate this on CPU, but this probably is very slow. So let's see what well, it may be slow. Let's see what happens if we allocate this buffer in the host visible memory, just as an experiment. Yes, our calling time increased like 2x. We had like 0.14 or something, and now we have 0.26, if I'm not mistaken. Yeah. So that is not great, right? Like, we could allocate this buffer on the CPU, and then we could just read the data from it after the frame has ended. But then it's slower. Oh, maybe now atomics actually make a difference. Let's see. Let's do this vsync test again, or atomic ballad test again. So disable vsync, run this code, 0.14 for culling. Switch the counter buffer. We can like add another buffer, but then filling that might be as slow. So memory property, host visible. .26, right? Let's enable ballad. See if that is faster. Nope. 0.28. So that doesn't inspire confidence, right? Yeah. So that means this is probably a bad idea. We could do like a post-process pass on this buffer, add things up. Yeah. But then that has the same problem, which is that it'll take time. It's actually interesting that it takes so much time. But I guess, yeah, this is like atomics from the GPU into global memory. We could change our shader a bit to make things like that more efficient. Maybe? Maybe not. So yeah, we can explore the option. Like, it would be nice to also see the number of objects that we have that are called, but maybe the number of triangles is a more important goal. So let's do that. So when we create a query pool, right now we create a timestamp query. So let's change that by creating a second pool. And when you create the pipeline statistics query, then you are supposed to specify flags. Let's just specify all of them for now. Let's see what happens. I don't need all of this information, and it might be slow to like get this information. Like, we might be slowing down our rendering by gathering this information in the first place. But let's see if that's true. We aren't using tessellation or geometry shaders, obviously, and we aren't really using vertex shaders or input assembly, the mesh shading pipeline, but still, I wanna, like, let's start with that. So this will be the VK query type timestamp, right? Timestamp. Okay. And let's call this query pool timestamp. Yeah. And then let's create a second query pool. Let's call it pipeline. It's pipeline statistics, really, but it's too long. And we only really need probably one element here. I would guess. And let's switch to debug because we'll get validation errors. So so then at the end we wanna call, and I don't know what the format of the values are, or is rather, vk query type pipeline statistics. Let's see. Whoa, what? Okay. Interesting. We might decide that we don't like this feature. Have I committed the code, by the way? Okay, good. Yeah, like what's the... It's annoying that this documentation, or rather spec, doesn't explicitly say like what this, how do you retrieve the data? Like, is it the case that if I enabled like 7 counters, I just get them in order as 32-bit integers, or what? Like why is this not there? I don't understand. And I'm sure it's somewhere, it's like buried in this documentation somewhere. Oh, okay, yes, it's buried in this documentation somewhere. One integer value for each bit that is enabled, and it is written in bit order. Okay, okay, cool. Alright, so this was like timestamp results. And then we'll have pipeline results, really pipeline statistics results. Not sure how big it should be yet. Let's figure it out later. And I don't want these flags. So we are specifying 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 bits. A lot of these guys will be 0, but it doesn't matter. Oh, let's probably like this. So then you're supposed to like end the query or something. Query pool pipeline 0, and then before the frame like here. That 0, and then flags. Okay. I don't know, I never used that. Let's see if that works. Yeah, the vsync thing again. Damn it. Okay, let's do this without the vsync for now. Or rather with the vsync. Yeah, so this asks us to enable this feature. Let us do that. Not every device supports this, so ideally we need to check if it does. I will want to measure the GPU time before and after, and I'm also not sure, there was this thing about the inheritance flags or something. Maybe that's missing validation, but let's see if the data is not 0. Oh, let's do this, and actually here, let's do this as well. And let's put a breakpoint here and see if the data is even there. Some data is there. That is encouraging. One of these numbers fluctuates. That is not encouraging. Number 7. Zero, 1, 2, 3, 4, 5, 6, 7. Interesting. Okay. So I guess there's some NVIDIA like optimization that can reject fragment shader invocations in some cases, but it's not like, it's not deterministic essentially. So let's see, so this is saying that we have 32,000 input assembly vertices and primitives, which is a lie. We are not using input assembly. So that is good to know. This is saying that we have 1 million vertex shader invocations, which again is a lie. We are not using vertex shaders. Like, we are using vertex shaders in a different path, but not in this path. No geometry shader invocations, that part is not a lie. Clip-in invocations and primitives. So I think clip-in invocations is the number of triangles that got into the clipper, and then primitives is number that got out. So this is saying that we are rendering 64 million triangles, which might be reasonable. Can I look at the title? Yeah, okay. So this is saying 856, but this is before all sorts of culling that we do, including the mesh shader backface culling. So that is reasonable. And then it's saying that there is 500,000 fragment shader invocations, which may very well be the case. And then it's saying that there is tessellation evaluation shader invocations, which is a lie. We are not using tessellation shaders. And then it's saying that there is like 1 million compute shader invocations, which is actually also a lie. Did we divide the thing, or did we not just not divide the thing? No. Or I guess invocations, does it count threads or something like this? That would be weird. Interesting. Yeah, so this sounds like it counts, interesting. It sounds like it counts the invocations that got to the end of the compute shader, because we are doing culling on 1 million elements. Oh no, 1 million is divisible by 32, never mind. Yes, so this is correct. So it looks to me like when you enable pipeline queries with the mesh shading pipeline, some of the numbers are weird. Maybe because they are assuming that, you know, some other bits are enabled. Let's look at the more traditional workflow. So this is without mesh shaders. Okay, yeah, so this makes more sense. So this is saying that there is like 200 million vertices that we are feeding into input assembly, 68 million primitives, 62 million vertex shader invocations. This makes sense. This is basically saying that we... Yeah, so this is saying that we could have transformed 205 million vertices, but we actually only transformed 62.4. So this means that we have a 62.4 over 205.33. No, that cannot be true. Hold on. Oh yes, right. I need to divide. Yeah, okay. Alright, so this means we have like 0.9 ACMR or something like this on NVIDIA, which is not unreasonable. No geometry shader, some clipping stuff, 65 million triangles again, roughly speaking. And then fragment shader invocations, no tessellation, and then yes, coming. Yeah, so it looks like when you enable mesh shading, some of these counters are actually corresponding to task shaders or tessellation shader or something like that, which presumably is because some of this hardware is shared between the old pipeline and the new pipeline, so it just counts like stuff that is not really, yeah. Okay. So the number of triangles is basically this, and this is number of triangles that survived the clipper. So we could really render either. The 68 to 65 is a reasonably sane ratio. So if you disable culling, let's try that. Disable culling, things are really slow. Yeah. So now we are seeing that without culling we are feeding, is it 4 billion? 4 billion triangles into the GPU, and then 200 million survive, which means that when we do frustum culling, we are culling way more. Oh, this is because our draw distance is shorter, probably. Yeah. Which means that we really should be doing culling, and I guess we are, so that's good. Okay, so the pipeline statistics seem to work. So there's two questions that I have. One is that there is this inheritance info that I didn't really get. When the secondary buffer is executed, so in the primary it doesn't matter. Okay, so I don't have to worry about this. And my only other question is the fact that we are enabling these stats making our rendering slower or not? Like, does counting these things have a cost? So this is 5.15 or something like that. And now let's do begin query end query. Let's just like end the query immediately after we begin it, so that all numbers should be 0. Okay, so it looks like counting these things is free. So then, yeah, let's just count that. This seems fine. Let's count this around the render pass, I suppose. Hold on, where's this thing? And instead of doing 11 pipeline statistics bits, and I think we can initialize this like at any point, or for any query. Well, but it's cleaner to do it like this, I suppose. So we only really need like this or something like that. We don't need anything else. And then here we will just say that this is our data, and then our triangle count is not that, and instead yeah, and to count the draw call count that survived, we'll need to copy out of the GPU side buffer, unfortunately. So we'll need to do something like, yeah, we'll need to like create a second buffer and copy stuff out of that. So it would be like host buffer also 4 bytes, but then that thing needs transfer source. Yeah, I don't want to do this right now. I think it's fine. We'll just assume that the draws per second is the number of things that we feed in, and the triangles per second is the number of things that survive the culling. So that's good enough. So yeah, so now we see that we are submitting 67.5 million. We are running at like 13 billion triangles per second. If we disable level of detail, we are running at 17 billion triangles per second, because probably the LODs that are really far away aren't as optimal in terms of pushing the raw geometry throughput. So that is good, and then we can disable the mesh shading pipeline, and then disable LOD, and then enable LOD, and that's all good, right? So now our stats make more sense, which is what we wanted. Okay, cool. So let's commit that. Hope, you know, Intel adapters that our code did run on before support this feature, and then this does work. Yeah. Use pipeline statistics query to count triangles. Maybe it would have been nicer to do like host buffer and stuff like that. Yeah. Because it's kind of weird, but we'll do this. We will not do this today. We might remove this feature later in favor of a compute shader that does this analysis. The nice thing is that this should change, maybe, yeah, this should affect, like this number should be updated based on whether mesh.culling calls away back faces or not. But the non-nice thing is that it may or may not use some existing hardware counter that's free, and if it's not free, then it may introduce performance overhead. I don't know. It probably doesn't really introduce performance overhead, so maybe it's fine. So maybe we will not remove this feature. That's fine. This gives us more precise triangle counts that are affected by LOD selection and culling. Right, so for example, right now we have 67.5 million triangles. When we disable LOD, we are jumping up to 427, right? So we are reducing like almost 7x, 6.5x or something like that, the number of triangles in the scene using level of detail, and we don't really see substantial differences. So that's nice. All right, so yeah, that's all I had. Let me look at chat if there are any last minute questions, and we will end the stream. Do I have some Visual Studio plugins, or do you have to learn general keyboard shortcuts? No. So I am using a plugin. No. I'm using a plugin VS Vim, which is basically Vim inside Visual Studio. I have started using Vim around 8 years ago, so 8 to 9 years, and at this point it's really hard for me to use any editor that doesn't work like Vim. So I have to use plugins that emulate Vim and basically every editor that I use. So it's not just Visual Studio keyboard shortcuts. It's like a completely different way to edit code, which is why some of the stuff that like whenever I edit some things, I could do like this, right, in just a couple of keystrokes, and then change the usage to something else, right? But that is not something that's built into Visual Studio, that's Vim. All right, thank you guys. This has been a good stream, even though it's slightly, I guess I slightly pushed it over. I should have maybe ended before the pipeline statistics query, because I'm somewhat tired now. So yeah, good progress this weekend. I don't know exactly what we'll do next weekend. I thought in general I want to do occlusion culling, but I think it might be too early. So I think I will figure out what we'll do and we'll do something else. Maybe textures, maybe something else. All right, thank you, and see you guys next weekend. No, next weekend is fine. I think the weekend after next weekend there will not be any streams, but I think next weekend is fine. All right.